Alright, so we're in Advanced Math, Unit 1, Lesson 4, which is over radicals and rational exponents. And we are going to really kind of dig deep on this, even though it's a review and we should just gloss over it. I want to be sure that you understand radicals. I don't want you to just limp your way through them because they're not that hard, and this really will help you later on. It's fine to be able to do them on a calculator, but you need to understand what the calculator is doing, because most calculators are fairly limited in what they can do with a radical. And we'll talk about that later on. But for now, here's a list of all the numbers 1 through 10. This is a list of the squares of that number. That means I multiplied that number times itself 2 times. Cube means you multiplied that number times itself 3 times. A fourth means you multiplied it times itself 4 times. So if you need to pause the video in order to write this down on your guided notes, feel free to do so now, because I'm going to move on into the next thing. Understanding the real difference between these two expressions is going to help you. 7 squared tells you to do something. It tells you to multiply this base times itself twice. So that's why you get 49. Now, a radical, and remember, if there's not an index up here, it's understood to be 2. If it's anything other than 2, you will have the number there. So no number means 2 or square root. This asks you a question. It says, what number did you multiply times itself to get that radicand? And remember, these two numbers have to be the same. So the actual square root of 49 would be 7. This asks you a question. It says, what number did you multiply times itself 3 times to get 8? Well, what number would you multiply? In fact, you can look on your chart. A cube, 8, the root is 2. So the cube root of 8 would be 2. So remember, an exponent tells you to do something. A radical asks you a question. Okay, let's look at example 1. Simplify the square root of 252. Now, a radical is not in simplest form if the radicand has a factor that's a perfect square. So what you have to do is check your numbers and see if any of these will go into 252. And you can just do that with a calculator. You can start down here and work your way up. You can start down there and work your way back. If I start here, let's say I do 4. 252 divided by 4. That gives me 63. So I could break this up into 4 times 63. Now anything that's a perfect square, you can take the root of it, convert it, and pull that out from under the radical sign. So, and you don't have to write it down like this every time. What's the square root of 4? Well, that converts to 2. So now I have 2 times square root of 63. I know what you're thinking, just hang on. Is there a perfect square that'll go into 63? Yes, there is. I can do it again. I can simplify it some more. 63 will break down into 7 times 9. Now what's the square root of 9? 3. So when I pull it out, now I have 2 times 3 on the outside, which is 6 square root of 7. Now, this was the long way to do it. If I had been smart, if I had started from the end and worked my way down, maybe I would have tried 36 first. I would have said 252 divided by 36 was 7. I could have started off with 36 times 7. What's the square root of 36? 6. So it gets to come outside of the radical and do 7. Okay? So you still get the same answer. Always check your radicand. Even if you factored something out, check it again to be sure that you have gotten the most out of it that you can. Okay, let's look at example 2 now. I have -5 times the cube root of 128. Now this time I'm only interested in factors that are perfect cubes. So, like, will 2 go into 128? Yes, it will, but 2 is not a perfect cube, so I'm not interested in that. In fact, this time I am going to start at the end, or I'm going to start where it obviously would be too much. And I'm going to work my way back to see if I get the largest number first. 125 obviously won't go into 128. So let's go to 64. Now I'm going to have negative 5 times whatever I managed to pull out from under there. So will 64 go into 128? Well, yeah. 64 times 2. Okay? Now, I can pull the cube root. I can take the cube root of 64, which is going to be 4, out. I'm going to have negative 5. Now I have 4. What do I have left under there? 2. Then you multiply these two together. Negative 20, cube root of 2. Okay, example 3, 2 times the 4th root of 48. Now this time, I'm only interested in numbers that are perfect fourths. So I'm going to start here. That's too big, that's too large. So will 16 go into 48? Yes, it will. So I can rewrite this as 3 times 16. Now, what's the 4th root of 16? I've got this 2. The 4th root of 16 is 2 also. The 3 is just going to have to stay under there. I can multiply these two together, so I get 4 times the 4th root of 3. Okay, let's have a little bit of a discussion about radicals with variables before we move into the next set of problems. What's the square root of x squared? Well, it's x. Why is it x? Because where did this come from? Well, it came from multiplying x times x. That's its root. Remember, when you multiply bases together that have exponents, what do? You add the exponents. So you're asking yourself, what could I add to itself to get this 2? Well, that would be your 1. All right, let's look at this one. What if I want to find the cube root of x cubed? Well, you would ask yourself, this started off as x to the what? Well, that would be all 1s, because when you add the 3 of them, you get x to the 3rd. Therefore, the cube root of it is just x. You can kind of conclude here that anytime your index matches your exponent, they cancel each other out. Okay, or they divide out to 1. Now, let's look at the square root of x to the 6th. This is asking me, what number did I multiply times itself twice to get 6? Well, that means there was an exponent that matched, and when I added it together, I got 6. So what would that be? X to the 3rd. Isn't x to the 3rd times x to the 3rd? You add your exponents and you get x to the 6th. Okay? So let's look at x to the 8th. This is saying, what exponents of x could I add together to get the 8? So that would have been x to the 4th times x to the 4th. So the square root of x to the 8th is x to the 4th. Now let's look at this one. A cube root means that I multiplied that root times itself 3 times. So there must be some number, an x, with an exponent, that when I add all 3 of these together, and they have to be the same, I get 9. What number can I add to itself 3 times and get 9? 3 plus 3 plus 3. Okay? Now, there's also a pattern here. Just like these, when they matched, divided out and gave you an exponent of 1, these also divide out. Look at the pattern. X to the 6th, this index was actually 2. 6 divided by 2 was 3. 8 divided by 2 was 4. And 9 divided by 3 was 3. You can even expand this out. If I wanted, say, the 5th root of x to the 25th, you can still divide. That would give you x to the 5th, 25 divided by 5. Okay, I want to find the square root of 121 x to the 5th y to the 6th. So let's see what can we pull out. Well, the square root of 121 is 11. All right. Now, this is interesting because my index here is 2. This is a 5. 5 divided by 2 is not a whole number. That's not nice. So let me show you how to do one where you have an exponent that is not a multiple of your index. You're going to do the same thing that you would do with a whole number. If I have x to the 5th, what is a number just less than 5 that is a multiple of 2? Well, that would be x to the 4th. So you're going to break that up into x to the 4th times x. That's still equal to x to the 5th. Now what's the square root of x to the 4th? Divide 4 divided by 2. So that gives you x squared. Now that x is going to remain under the radical sign. All right, y to the 6th, you've got a 6 over 2. So that would give you y to the 3rd. And this would be your simplified answer. Okay, let's look at example number 6. Negative 2p times the cube root of 648 p to the 5th q squared. And you can see I wrote my list of perfect cubes up here. You do need to have your perfect numbers written somewhere that you can pull out whenever you're working on roots, or you just need to make one. Make a little chart every time you're going to deal with roots. So negative 2p, I'm not going to do anything with it yet, but I don't want to lose it, so I'm going to put it in parentheses and leave it out here. Alright, let's start first with 648. I want to know what's a perfect cube from my list that will go into this. So I started with 343. When you divide 648 by 343, that's a decimal. Alright, 648 divided by 216 gives me 3. So I'm going to factor this. I'm going to rewrite it as factors of 216 times 3. And I'm going to go ahead and factor everything else that's necessary because p to the 5th power, remember we concluded that you can divide an exponent by your index and get, the root of it. Well, 5 won't divide evenly by 3. And I don't want to deal with a fraction exponent right now. But what you do is you factor this. What number is a little bit less than 5 but is divisible by 3? Well, p to the 3rd. Now you can't lose value, so p to the 2nd. P to the 3rd times p to the 2nd is worth the same thing that p to the 5th is. I'm just reformatting it so I can deal with it. Now q to the 2nd. Also not divisible by 3, but I can't even back it down. 2 is smaller than 3. So what I'm going to have to do with that is just leave it like it is. Now I'm ready to pull stuff out. I don't want to forget this negative 2p I have out here. And I'm going to go ahead and put me a radical over here because some things are going to stay, some things will come out. Now the cube root of 216 is 6. And 3 is going to have to stay under there. The cube root of p to the 3rd is p. P squared will have to stay under there. And q squared will have to stay. Now let's simplify this part. Negative 2 times 6 is negative 12. P times p is p squared. And then I have all this stuff here that could not come out from under the house. Okay? Okay, let's talk about the rules for addition of radicals. Addition, subtraction is the same thing. You use the same theories behind adding things with variables and exponents. Remember, radicals are just the opposite of exponents. So what would you get if you added 2x plus 3x? You're going to get 5x. Remember, when you add bases, you never change the exponent. So you're not going to get 5x squared. Alright, 2x squared plus 3x squared. You use these to match. You add the coefficients and the exponent stays the same. Alright, it's going to be the same thing with a radical. If the radical part matches, and I mean it has to have the same radicand and the same index, then all you do is add the coefficients. So 2 plus 5 would be 7 square root of 2. Right here, I have both of these have cube root of 7, so I could just add the coefficients. So that's going to give me 11 cube root of 7. The radical part does not change. You only use it to match. Now let's look at what you cannot do. Here I've got 3 square root of 2 plus 2 square root of 3. The radical parts don't match. So this is already simplified. This would be your final answer. Here I've got 5 square root of 2 plus 3 cube root of 2. The indices don't match, so you can't add that either. So that is lowest form there. Okay, let's look at example 7. We have negative 5 square root of 32 plus 7 square root of 18. And I just got through telling you that these two things have to match. So since these don't match, you're probably thinking you can't add them. But there is a trick, or there's another rule. Your radicals have to be in simplest form. So what we did in the last section, simplifying radicals, you have to do that first before you can say those don't match, I can't add them. So let's simplify square root of 32. Is there a perfect square that will go into 32? Well, 16 will. I can break that down into 16 times 2. I'm going to pull the 4 out. The square root of 16 is 4. And I have square root of 2 left. So this is negative 20 square root of 2 when it's simplified. Now let's do the same thing to 18. Is there a perfect square that will go into 18? Well, 9 will. 9 times 2. So I'm going to have 7 times. The square root of 9 is 3. And the 2 stays under there. So now I have 21 square root of 2. Now your terms match. So you can combine the coefficients. Negative 20 plus 21 is positive 1, which is understood. So your final answer there would just be square root of 2. Okay, let's look at number 8 now. Once again, we have 3 terms here. We're going to have to simplify them before we can combine. So I am looking for perfect squares that will go into 24. That's going to be 4. So I can rewrite that as 4 times 6. Now the square root of 4 comes out. So I have 2 times 2 square root of 6, which is 4 square root of 6. Now, as you get more comfortable with this, feel free to start skipping a step ever so often, primarily this one. Just don't skip too many because it's going to be hard to go back and find your mistake. So you do want to write enough steps that you can see where you messed up if you don't get the right answer. Alright, minus, what is a perfect square that will go into 12? 4 again. So this will break down into 4 times 3. Now let's skip that step. What is the square root of 4? 2. When I pull it out and multiply it times 8, what do I get? 16 square root of 3. And I'll just go ahead and copy it down here so we're all on the same line. Okay, now the last one. What is a perfect square that will go into 54? How about 9? So this is going to factor into 7 onto the square root of 9 times 6. Alright, what's the square root of 9? 3. So when I pull that out and multiply it times 7, I'm going to get 21 square root of 6. Alright, so now what matches? This matches this. 4 plus 21 will give me 25 square root of 6. Now what about this? Well, nothing will combine with it, so it's just going to have to stay like it is. Okay, here's example number 9, and we're dealing with cube roots this time, so we're going to be looking for these numbers. Now I look at the first one and I say, now when you take an odd root of a negative, you're just going to have a negative when you come out. Like negative 1 times negative 1 times negative 1, you reclaim that negative. So what would be a perfect cube that will go into 56? How about 8? So we can pull out negative, or we can rewrite this as negative 8 times 7. Now what's the cube root of negative 8? Negative 2. So we're going to have negative 3 times negative 2 times the cube root of 7 plus, alright, down here, a perfect cube that will go into 189. Well, I know 125 won't go, 64 won't go, 27 will go 7 times. So I'm going to factor that as 27 times 7. Alright, the cube root of 27 is 3. And then to simplify this, negative 3 times negative 2 is 6. So I have 6 onto the cube root of 7 plus 3 onto the cube root of 7. Adding the coefficients, or the numbers out here, 6 plus 3 is 9. Cube root of 7. So simplify and then add the coefficient number. Okay, let's have a look at problem number 10 now. So I've got to simplify. Let's just focus on this one first. The 4, put it out there. Is there a perfect square that will go into 72? And I start working my way down the line. 36 times 2 is 72. So I'm going to rewrite this as 36 times 2. Now, look at that x to the 5th. Remember what we did there. When you have an exponent that is larger than your index, you can pull it out. So what is a number less than 5, but that's a multiple of 2? How about x to the 4th? Okay, so we can break that up into x to the 4th times x. Now let's pull out perfect squares. I've got the 4 here. What's the square root of 36? 6. And the square root of x to the 4th? X squared. Now the other things, the 2 and the x, will have to stay under there. Alright, and then let's go ahead and simplify this. 6 times 4 is 24. X to the 2nd, square root of 2x. Alright, down here. 3x is going to stay like it is for right now. Now what's a perfect square that will go into 242? So I start backing down. Oh look, 121 is half of this, so I can write that as 121 times 2. Alright, here I have an exponent of 3. It is larger than my index, so I can back it down to a number that's a multiple of 2, and that's just going to be x squared times x. Alright, now what is, let me carry the 3x here, what's the square root of 121? 11, so I can cross that off. 2 is going to have to stay under there. The square root of x squared is just x, and the other x will stay under there. And then to simplify this, 3 times 11 is 33, x squared onto square root of 2x. Okay, now since our radical parts match, that is not going to change. It's just going to stay the same, but I can combine these two. Now since the x squareds match, all I have to do is subtract exponents. Now 24 is less than 33, so my answer is going to be negative 9 x squared. Now we're going to look at multiplication. With multiplication, all it has to match is your indices. The index has to match, and since both of these are square roots, they match. Then you multiply everything that's on the outside of the radical and everything that's on the inside together. So the process would be 2 times 5 would give me 10. 3 times 7 would give me 21. Now, you have to check your radical and see if it can be simplified. And this one can't. I was just trying to show you the method there. So, you're going to multiply things that are outside the radical, you multiply things that are inside the radical, and then you simplify the radicand if necessary. Okay, here's number 11. We have a negative times a positive, so naturally our answer is going to be negative. Now, the number outside here is a 1, so when you multiply that times 2, you're just going to get a 2. Alright, 18 times 20 will give you 360. That's all the multiplication. Now we're just simplifying. What's a perfect square that will go into 360? How about 36? 36 times 10. Now what's the square root of 36? 6. Pull it out and it's going to multiply times the number that's already out here. So you have negative 6 times 2 is negative 12. Square root of 10. Check your radicand. Be sure that it is lowest terms, that there's not a perfect square that will go into it. Okay, here's number 12. So this time we have cubes. It's still the same thing. Since the cubes match, the indices match, we're going to multiply what's outside. So 5 times 1, just be 5. And then we can multiply what is inside. 36 times negative 12 will give us negative 432. Alright, now let's simplify. What is a perfect cube that will go into negative 432? How about 216? So this is going to be negative 216 times 2. Now, the cube root of 216 is 6, and since it's negative, when you take the odd root of a negative number, that number just becomes negative. So we've got 5 times negative 6 times the cube root of 2, and 5 times negative 6 is negative 30, cube root of 2. Okay, let's work problem number 13. So we do have matching, the indices match, so we can multiply the stuff that's outside and the stuff that's inside and then reduce. 7 times 3 is 21. That was not a problem. Alright, 3 times 15 is 45. X times x to the third is x to the fourth, and y to the second times y is y to the third. Alright, we are back to simplification. What's a perfect square that will go into 45? Well, how about 9? So I'm going to factor that into 9 times 5. Alright, x to the fourth. Remember, we have a 2 here, so we want multiples of 2. X to the fourth is fine, just like it is. But y to the third is 1 too many. So I'm actually going to have to break this back down to where it came from, but that's fine. Alright, let's pull out. The square root of 9 is 3, so I used that. 5 will have to stay under there. The square root of x to the fourth is x squared. The square root of y squared is y, and then I've got that y left under there. So let's simplify this. 21 times 3 is 63, x squared y, all onto the square root of 5x. See, you're probably getting the hang of it by now. Okay, here's number 14. Got the square root of 3 times the square root of 6 minus the square root of 24. So we're going to have to distribute. We're going to use some of these newer techniques with some stuff we already know. We know how to distribute. Now we know how to multiply radicals, so we're just going to combine the two. They do all have the same index, so that's not a problem. When I distribute here, now remember, things that are outside multiply together, so 1 times 1 is 1. Things that are inside multiply together, so 6 times 3 is 18. Alright? Positive times that minus gives you minus. 1 times 1 is 1. Square root of 3 times square root of 24, when you multiply 3 times 24, that's going to give you 72. Okay? Now, they are subtracted. They do have the same index, but before I can say, well, you can't combine those, I have to simplify them. Is there a perfect square that will go into 18? Well, 9 times 2 will. What's the square root of 9? So we've got 3 onto the square root of 2 minus. All right, let's simplify this side. What's a perfect square that will go into 72? 9 will, but I think something larger than 9 will. How about 36? 36 times 2. What's the square root of 36? 6 onto the square root of 2. Now, the radical parts match, so all you have to do is combine those two coefficients. Positive 3 minus 6 gives you negative 3 onto the square root of 2. Okay, let's look at number 15. Now you have binomial times binomial. So you can use your FOIL method or you can just call it distributing. But you need to be sure that you multiply the first one times the first one times the second one, this second one times the first, second times second. So now everything that is outside of a radical can be multiplied together. Everything that is under a radical, as long as it has the same index, can be multiplied together. So 5 times 7 square root of 2 is going to give you 35 square root of 2. I just multiplied the 5 times the 7. Alright, 5 times 1 is just 5. Alright, let's go to this one now. A negative square root of 2 times a 7 square root of 2 is going to be negative. Now the 7 won't change, but square root of 2 times square root of 2 becomes square root of 4. And then square root of 2 times 1 is just square root of 2. Alright, let us simplify. First, go through there and check all of your radicals to be sure that they are in simplest form, and that means that there's not a perfect square that will go into them. Now this one is fine, so we're not going to change it. 5 doesn't have a radical, so that's fine. Here's where we come to one that needs to be simplified. What is the square root of 4? Well, that's just 2, and 7 times 2 is 14. Then this square root of 2 is fine. Now we can combine all the terms that have matching radical parts. So 35 square root of 2 minus the square root of 2 gives you 34 square root of 2. Remember, this has the understood 1 out there. And 5 minus 14 is minus 9. Okay, let's look at number 16 now. We have a binomial squared, 7 minus 2 square root of 3 squared. When you square a binomial, you don't just square each term, you have to expand it out. And that means I'm going to multiply 7 minus 2 square root of 3 times 7 minus 2 square root of 3. Now you need to distribute or FOIL. So you want to multiply this number times both of those and this number times both of those. Remember, things that are outside the radicals can multiply. Things that are under the radicals can multiply together. So 7 times 7 is 49. 7 times minus 2 square root of 3 gives me minus 14 square root of 3. The 3 can't change. Alright, negative 2 square root of 3 times 7 is another 14 square root of 3. Alright, when I multiply negative 2 square root of 3 times negative 2 square root of 3, first of all, it's going to become positive. 2 times 2 is 4, and square root of 3 times square root of 3 becomes 9. Now we need to go through here and simplify all the radicals if necessary. This one is simplified, this one is lowest terms, but this one can be converted to a 3. So now if I want to simplify that part just a little before I continue on, 4 times 3 will give me 12. Now, these two have matching radicals, so I can combine them. Now remember, there's a difference between multiplication, division, addition, subtraction. When you add and subtract, the radical part is used to match, but it doesn't change. So what we're going to have here is 49. Minus 14 gives you minus 28 square root of 3. Alright, now what else can I combine? 49 and 12 would give me 61 minus 28 square root of 3. Okay, and that's going to be your final answer. Before we look at the next section, I want to go over these two different cases because there's actually two ways to solve problems that have radicals in a fraction. And which one you choose depends on what you have. So you're going to have to make a judgment call here. You can either combine the radicands under one radical sign and then simplify, or you can simplify first and then combine. And this is what I mean. If I have this problem here, both numerator and denominator are, first of all, they are perfect squares. But 49 won't go, or 4 won't go evenly into 49. I can't divide 49 by 4. So the way you would want to solve this problem, since 49 is not a multiple of 4, what is the square root of 49? 7. And what is the square root of 4? 2. So your final answer here would just be 7 over 2. Now watch the difference here. These two numbers, it looks like the same scenario, but 50 and 2 are not perfect squares, number one. But I can divide 50 by 2. So what I would want to do on this problem is put the whole fraction under one radical. Now that's only if your two indexes match. So what you would have here is 50 over 2 under one radical. Then you could divide. 50 divided by 2 is 25 and get 5. So whether you find the square roots and then make a fraction, simplify if possible, or do you simplify first and then take the square root, depends only on the numbers that you have. So you're just going to have to look at each problem and make that call yourself. Okay, this is example 17. So what we want to do here is kind of assess our situation. We look at the two coefficients of the radical, or the numbers outside, and right off the bat I see that 6 divided by 2 will reduce down to 3. So let's just go ahead and take care of that. Now let's look at just our radical part. I see this 6. 6, number one, is not a perfect square. So it's going to be better for me if 6 will go into 480. Will 6 go into 480? Because what I'm doing now is I'm saying, all right, this is 3. I got my 3 here. Times, and I'm going to put both of these under the same radical now. What is 480 divided by 6? Just 80, okay? Now you have to simplify. Is there a perfect square that will go into 80? And I'm thinking, let me go through my numbers here. I know 4 will go, 4 times 24 will go twice. So 80 is equal to 16 times 5. So I'm going to do 16 times 5. Now what's the square root of 16? 4. So when you pull that 4 out, now you have 3 times 4 times the square root of 5, which is 12. Square root of 5. Okay, let's look at number 18 here. First of all, the numbers on the outside won't reduce down, so I'm just going to come over here and put the 7 over 2. Alright, now let's look at our radicals. They're cube roots, so do I have perfect cubes? No, I don't. Next, I ask myself, will this number go into the top number? And yes, it will. So what I'm going to do here is, and this is a cube root, I'm going to put negative 32 over 4. I'm going to combine, divide, then simplify. So I've got the 7 over 2, the cube root. Negative 32 over 4 is negative 8. Alright, now I have a negative sign under a cube. So that means, I'm just going to put this out here and I'll multiply it. Means when I pull this out, it's going to be negative. If you take the cube of a negative, it's negative. Why? Because cube means multiplying it times 3. And if you multiply 3 negatives together, the first two make a positive, but the last one makes it negative again. So the cube root of a negative number is negative. Now, what is the cube of 8? The cube root of 8? 2. So how do you multiply these two together? Well, negative times positive is going to be negative. This is like 2 over 1. 2 times 7 is 14 over 2. So, final answer is negative 7. Okay, let's look at number 19 now. I have a cube root of this big fraction. So, what I'm going to do first is I'm going to go in here, since these are not perfect cubes, I'm going to go in here and I'm going to simplify the whole fraction first. So the index is not going to change. It will still be cubed. 288 divided by 2 is 144. All right, j to the 7th over j to the 2nd. Remember, you subtract exponents. The largest one is on top, so it's going to stay on top. And k to the 4th over k. You're still subtracting exponents, so now you have k to the 3rd. All right, now what I'm going to do for my next step is I want to isolate, or I want to factor out any perfect squares. So is there a perfect square that will go into 144? Well, 8 will. So I'm going to rewrite 8 at 144 as 8 times 18. J to the 5th. Now this is one of those we looked at just a few problems ago. Anytime you have an exponent that is larger than your index, you need to take out the multiples of the index. So if I back it down, you can't go up, but I can back it down. What is the next smallest number from 5 that will divide evenly by 3? That's just going to be a 3. So what I'm going to do is I'm going to split j to the 5th up. I'm going to make it j to the 3rd times, all right, what's left over after I take j to the 3rd out of this? Remember, you were adding exponents, so to split it up, you subtract. Now, k to the 3rd matches this, so I'm going to leave k to the 3rd. Okay, let's see what we can pull out. Now, the cube root of 8 is 2, so I can pull that out. The cube root of j to the 3rd is j, and the cube root of k to the 3rd is also k. Now, everything else is just going to have to stay under the radical. So I'm left with 18 j to the 2nd. Okay, before we look at number 20, let's talk about what does it mean for a radical to be in simplest form. Now, the thing we've been talking about is that you cannot have any factors under there that are perfect roots. If you've got a square root, you can't have any perfect square factors. If you've got a cube root, you can't have any perfect third or cubic factors of the radicand. There's also another thing. Radicals in the denominator. Now, this is actually up for debate right now, so you just have to pay attention to what your teacher asks for. It's called an irrational denominator, and most of the time you want to rationalize it, but usually your teacher will tell you that they do want all denominators rationalized, or they don't care. So, this is what it looks like when you have an irrational denominator. You still have a square root under there. And I can't just simplify this. There's not a perfect square that'll go into 10. So how do you eliminate it? Now the trick is, it's fine to have a radical in your numerator in the top part. You just can't have it in the denominator. So what we're going to do is it's just going to kind of switch it. What have we learned about any time you multiply a square root times itself? If I do square root of 2 times square root of 2, I get square root of 4, which is 2. If I do square root of 3 times square root of 3, I get square root of 9, which is 3. Square root of 4 times square root of 4 is square root of 16, which is 4. Do you notice the trend? Anytime you square a square root, you just wind up with your original radicand. So we're going to use that just happens to happen to fix this. If I multiply square root of 10 times square root of 10, I get square root of 100, which simplifies to 10, right? Alright, that's fine and dandy, but you just can't go around multiplying willy-nilly wherever you want to. You have to justify it. Now when you have a fraction, you can multiply it times 1 and not change the value, right? Well, you can multiply the denominator by something as long as you multiply the top by that. This is what balances out that fraction, and you're not changing the value of it, you're just changing the way it looks. So when you multiply 5 square root of 10, alright, you get this. Now, can I simplify this? Yes. At this point, you would say, well, 5 will go into 10. You have 10 left over. So you have square root of 10 over 2. Now, can you reduce that? No, because the 2 is not under a radical. If the 2 were under a radical at this point, yes, you could reduce that, but it's not. So we're not going to be able to reduce it. This is going to be your final answer. So how do you rationalize a denominator? Well, you multiply that radical times itself. And what do you do to keep that balanced? You multiply the numerator times that same thing. So let's look at another one. Okay, this is sample problem 21. We have a radical in the denominator and we need to rationalize it. So what we want to do is we want to multiply by just the radical part, because there's nothing wrong with the 4. And it's going to be the radical in your denominator. I know you have a radical in your numerator, but that's fine. You can have a radical in your numerator. The only thing about this fraction right here that makes it illegal is that square root of 3. Whatever you multiply the bottom by, you're going to multiply the top. Now, we're just going to simplify this, and whatever we get is whatever we get. When I multiply here, remember the things under the radical can multiply together, so I get 6 onto the square root of 24. And over here, these two are going to multiply out and just be 3. Remember, if you multiply 2 radicals together, you just get the radicand. So now I have 4 times 3. All right, let's simplify. I've got 6 square root of 24 over 12. Now I'm going to go ahead, and you can do this in any order you want to. I'm going to go ahead and reduce this now. 6 will go into 12 2 times. So what I have is square root of 24 over 2. Now let's look at 24. Is there a perfect square that will go into 24? How about 4? So we're going to pull that out. We're going to rewrite this as square root of 4 times 6 over 2. What's the square root of 4? 2. So I pull that out. I've got 2 square root of 6 over 2. And yes, the 2's cancel. So your simplified form is 6. All right. And you could have done some of those steps in a different combination. You could have done them in a different order. As long as you're coming out with that square root of 6, you're good. Okay, let's look at number 23. Now we have a radical in the denominator. The difference is this time I have a binomial in this denominator. It's not just the radical. It's not this multiply this. It's a subtraction here. So just out of curiosity, let me show you what would happen if we use the technique that we just used on these other problems. What if I just multiplied this times square root of 5 over square root of 5? What's going to happen? Well, the top is fine. Got that. Now when I distribute this into this binomial, now I have negative square root of 5 minus, and yes, square root of 5 times square root of 5 is square root of 25, which is 5. But you see, I still have the radical in my denominator. I did not rationalize it. If you multiply it by a negative square root of 5, it's just going to keep jumping back and forth. So, what do you do here? Well, we have a different technique that's a little bit similar. Do you remember the word conjugate? Conjugate. A conjugate is a binomial with the opposite sign. So if this is your original binomial, the conjugate is x minus 3. If you've got 2x minus square root of 7, the conjugate is 2x plus square root of 7. Numbers stay the same, the signs is the opposite. Now, something very interesting happens when you multiply a binomial, especially one with a radical, times its conjugate. So let's just look at what happens. If I take this fraction and I'm going to, instead of just multiplying it by square root of 5, I'm going to multiply it by the conjugate. See, this is still the same thing over itself. This is still equal to 1. I'm just multiplying this fraction times 1. Now let's go ahead and multiply across the top. So when we distribute here, we've got negative 4 plus 4 square root of 5. Because we don't care what happens in the numerator right now. let's look at what happens when I multiply a binomial with a radical times its conjugate. So I'm going to do -1 times -1. That's going to give me +1. I'm going to go do -1 times square root of 5. That's negative square root of 5. All right, now negative square root of 5 times -1 gives me positive square root of 5. And negative square root of 5 times negative square root of 5, positive square root of 5, is going to give me negative square root of 25, which is 5. Now, this negative square root of 5 and positive square root of 5 subtract out. That's now 0. And 1 minus 5 is -4. So let me come under here, -4 plus 4 square root of 5 over -4. So can you reduce that? Yes, you can. I really should not have distributed it at this point because now I'm going to have to undistribute it. What's the greatest common factor? I'm actually just going to go back to 4 times -1 plus square root of 5 before I distributed it over the -4. So these two things cancel out and you still have -1. So that's going to be negative of -1 plus square root of 5. This will distribute in there and you get 1 minus square root of 5. Okay, this is number 24. 3 plus square root of 5 over square root of 5 plus 4. I see this denominator and I need to rationalize it. I know, I have learned that in order to rationalize a denominator, I'm going to multiply it by its conjugate, which is square root of 5 minus 4. Now, how do I know that? Because I've practiced it and I've memorized it. It's kind of like, how do you know to go when you get a green light? You've learned that. You know, that's not innate knowledge. You aren't born knowing that, but you learned it over time and through practice. Well, it's the same thing. You just have to practice this enough so that you realize when you need to rationalize a binomial with a radical in it, you will do that by multiplying by the conjugate. Then you know that anything you do to the denominator, you have to do to the numerator. So we're going to put that up there now. All right. Now this is just going to be simple full method or distributing. I've got 3 times square root of 5, so that's going to be 3 onto the square root of 5. All right, 3 times minus 4 is going to give us minus 12. Square root of 5 times square root of 5, square root of 25, which is 5. And square root of 5 times minus 4 gives you minus 4 onto the square root of 5. Okay. If you want to go ahead and simplify this top one, 3 square root of 5 minus 4 square root of 5 will give you, let's do the whole numbers first because you want to put the whole numbers in front. Negative 12 plus 5 is -7, and 3 minus 4 is minus 1 square root of 5. Okay? All right, now let's look at this bottom. Square root of 5 times square root of 5 is square root of 25, which is 5. So let's just put 5. All right, square root of 5 times -4 is going to be -4 square root of 5. Now let's do the second number. Positive 4 times square root of 5 is going to be plus 4 square root of 5. And positive 4 times -4 is minus 16. All right, your minus 4 square root of 5 and your plus 4 square root of 5 subtract out. That's now 0. 5 minus 16 gives you -11. Okay? Now, technically, you don't want a negative in your denominator, so you could multiply the top. There's a lot of different ways to look at simplifying that. I'm going to just look at it as multiplying top and bottom by -1, and what that's going to do is give you positive 7 plus square root of 5 over positive 11. Okay, number 25 says write in simplest radical form. So it's in exponential right now. It has an exponent. but I want to rewrite this in radical form. And we will look at some of the reasons why this will be easier later on in advanced math. But for now, let's just look at the process. All you have to do is remember the rule. You don't have to understand it. You just have to remember it. So I can take the denominator, that becomes my index, and the numerator becomes the exponent. Okay? Now, can you simplify this? Anytime the exponent of your radicand is greater than your index, you can simplify it. So is 9 greater than 2? Yes, it is. So how do we do that? Well, let's back it down. Remember, if we're looking for multiples of your index, since my index is 2, I want even numbers. So what is backed down from 9? What's the next even number? P to the 8. Now what would you have to multiply P to the 8th to make the value the same as P to the 9th? Well, P to the 1st. Alright? Now as far as simplifying this, we can combine, we can go back to this method. I can take my exponent divided by my index. So this is actually P to the 8 over 2. Now that P is going to have to stay where it is. So I have P to the 4th square root of P. Okay? Just go slow and do one thing at the time. Okay, example 26. Now we look at our problem. So, you know, you kind of have to look at it, see where you're going with it. I know that I have these fractional exponents and it says to simplify this. So let's put these in radical form. Now fortunately, the denominator in all three of these is the same. So I can convert these to one radical. And it's going to be a cube. So the denominator comes over to be your index. Now remember, your numerators remain and they become the exponent of that base. So I've got 27 to the first power, which is just 27. I've got R to the 17th, and I've got S to the 8th. Okay? Now, let's break it down and simplify it. Is 27 a perfect cube? And yes, it is. The cube root of 27 is 3. So I can pull that out. Now I took care of that. What about the 17, the R to the 17th? Remember, what you look for now is multiples of your index. So what is a multiple of 3 that is close to 17 without going over? Well, how about 15? So I could have R to the 15th, R to the 2nd, right? Let's go ahead and do S. What is a multiple of 3 that is closest to 8 without going over? Well, how about S to the 6th, which would leave us S to the 2nd. You see how I just wrote both of these as the exponents will add up to give me my original. Now, take the one that's the multiple. 15 divided by 3 gives you R to the 5th power. So I've used that. And S to the 6, 6 divided by 3 is S to the 2nd. Now, let's see what we have left under the cube root. I just used that one. So we have R to the 2nd, S to the 2nd. And as strange as it looks, that's going to be your final answer. 3, R to the 5th, S to the 2nd, times the cube root of R squared, S squared. Okay, number 27 says write in simplest exponential form. So that means we want a fractional exponent rather than a radical. Now, this one gets a little bit confusing if you're not paying attention because the 5 is not cubed. That's 5 times k to the 3rd. So what I do, put that in parentheses. What's actually the exponent of the whole thing? A 1, understood 1. So now convert this to exponential by, you're going to take your base, which is 5k to the 3rd, and you're going to put the 4 becomes your denominator and the 1 stays your numerator. Okay, number 28 also says write in simplest rational form. So we want to get rid of the radical. Now this one, the way the problem is written, it already has this base or this radicand in parentheses to the third power. So the whole base is grouped together and this is its only exponent. So to apply the rule, what we want to do is take the base, keep it in parentheses with that exponent. Now, according to your rule, your index becomes the denominator. What is the index here? 2. So that's all you got to do. Just know your rule. Be careful. Okay, number 29 just says simplify, and we're going to kind of be using some old rules in a new way. And we have two bases with fractional exponents, and they're multiplied together. Well, what do you do with exponents when you multiply the bases? X to the second times x to the third, what did you do with those exponents? You add them. So that's what we're going to do here. I'm going to add 3/4 plus 5/2. Now what do you need when you add fractions? You need a common denominator. The common denominator between 4 and 2 will be 4. So I won't change the top one, the first one. When I change this one, what did you multiply the old denominator by? 2. So you have to multiply the top by 2, so that's 10. So that's going to be 13/4. So this is 13/4. Now they do want me to simplify this into radical form. So now I'm going to use that rule where my denominator becomes my index and my numerator becomes my exponent. Recall, anytime you have an exponent under a radical sign that is greater than your index, you can simplify that. So, what is a multiple of 4 that is less than 13, as close to 13 as possible without going over? 12. So I would rewrite this as g to the 12 times g. Right, now you divide exponent by index. 12 divided by 4 is 3. So I pull out the 4th root of that is g to the 3rd, but I still have the 4th root of g left. Okay, here's number 30, and we want to write this in simplest radical form. So we're going to try to get rid of any fractional exponents. Now what do you do when you have exponents raised to another exponent? If I had x to the second to the third, what do you do with those two exponents? Well, you're multiplying. So that's what we're going to do here. We're going to take this 1/2 and we're going to multiply it times the exponent of each of these three numbers, and then we'll simplify them all down. Now what is actually the exponent of the 16? 1. So I'm going to start off with 16 to the 1/2. Now what is 6 times 1/2? Well, I can go ahead and just put 3 there. Alright, 3 times 1/2 on the B is still going to give me a fractional exponent. Okay, let's take each one in turn and simplify it. Now 16 to the 1/2 power actually means, remember, the denominator becomes your index, the exponent stays with the base. So what's the square root of 16? Just 4. Alright, a to the 3rd is perfectly fine like it is. Now let's look at this one. Remember, denominator becomes your index. Numerator stays with your radicand. Now, anytime your exponent is larger than your index, you have to reduce. So I can rewrite b to the 3rd as b squared times b. The square root of b squared is just b. And then what do I have left under there? That b. So this is what your final answer is going to look like. Okay, number 31. We have a fraction, matching bases, and rational exponents. We need to simplify those exponents. Well, what do you normally do with exponents? If you have x to the 5th over x to the 3rd, you subtracted, right? Well, we're going to do the same thing right here. So we're going to say m to the 3/2 minus, now this is a -2. So what happens when you have minus and negative? It changes to plus a positive. Now, what is 3/2 plus 2? Put your 2 over 1. You need common denominators, which would be 2. If I multiply this times 2 to get this, I got to multiply the top times 2. So I get 4. So this is going to be 7/2. So now I have m to the 7/2. Now remember what happens here when we convert this to a radical. The denominator becomes your index. The numerator is your exponent. If your exponent is larger than your index, you have to reduce. So what is an exponent that is less than 7 but the multiple of 2? Well, m to the 6th and m to the 1st. Now you can divide. 6 divided by 2, m to the 3rd. This m has to stay under the radical, so there's your final answer. Number 32, this is our last example problem, all right? So w to the 2/5 to the 10/3. What did you do if you had x to the 2nd to the 3rd? You multiply exponents, right? So I'm going to multiply 2/5 times 10/3. Just like any other fraction. You can go ahead and cancel here. 5 will go into 10 twice. So that gives me 4/3. So what I have is w to the 4/3. Now, your denominator becomes your index. Your numerator becomes your power. Anytime your exponent is greater than your index, you need to reduce. So I can convert this w to the 4th. I'm going to back it down to the closest multiple of 3, which is 3, and then subtract the exponents. 4 minus 3 gives me w to the 1st. Now, the cube root of w to the 3rd is w. And what do I have left over? The cube root of w. Okay, now it is your turn to practice, practice, practice. Go slow. Just do one thing at the time. Don't try to look at a problem and just write down the whole answer. Pinpoint one thing that you can do and do that thing, okay? Practice makes all the difference on these things.